All right, very good. So we will continue our discussion of the electrostatic and magnetostatic multipoles today, and we're going to look at a different technique for looking at the multipole expansion, at least two different techniques. So, and so you will be, and this part will be new. This is something you haven't seen before for sure. It's a quick, it's actually pretty powerful that you can do that. And it goes beyond, even beyond the standard uh, spherical mathematics that is used for solving partial differential equation in the spherical coordinate system, right? So the answers look similar, but the method is different. We're not looking at it as a solution of a differential equation. And so that's something in some sense powerful. So let me actually just list what we are going to discuss today. So first thing, of course, we last time we looked at the magnetic dipole vector potential, but we did not calculate the magnetic field. So we need to now calculate the magnetic field of a magnetic dipole. And then we will compare it with the electric field from an electric dipole, which we know, and we used Mathematica for plotting it. And then we will move on to spherical mathematics. Okay, so let's recall that so anybody remembers the definition of the magnetic dipole moment? Magnetic dipole moment it's given by, of course, a volume integral of essentially r crossed with j at each position r integrated over all volume of space. Right now, of course, you may have a localized magnetic dipole, and so the integral would simplify, and then the corresponding vector potential A of r would be mu0 over 4 pi m crossed r over r cubed for r much less, much greater than r, right? So this is the largest contribution coming from a field of localized currents, and field, I mean, a certain distribution, I should say, of localized currents, and that happens to be, just the vector potential. We need to now, of course, calculate the magnetic field. So how would we do that? Anybody remembers? You know this. How do I calculate the magnetic field if I know the vector potential? We introduced this, I think maybe a couple of classes ago. How are these two quantities related with each other? If you know the scalar potential, gradient of the scalar potential is the electric field, right? Negative gradient. That's what gives you the
curl of A is
curl. Okay, very good. Curl of A. And then that's going to be curl. So we will need to evaluate now curl of this quantity mu0 over 4 pi. That's of course constant. So that's going to come outside of the derivative. Okay, so that's what we need to do. And that means we have a cross product double cross product. So you need to use a back-cab rule to simplify this. So again, the vector calculus things that you are familiar with, they are important. So A, right? So let's call this A. This is vector B, and that's vector C. So you have A cross B cross C. Then the back-cab rule says it's going to be B multiplied by A dotted with C R over R cubed. Right? We're taking R over R cubed, the whole thing, as the vector there. 1 over R cubed is just a constant. Minus C. C in this case is just vector R over R cubed. And then you have AB. So A dotted with B, but in this case, you have to change the, or you have to preserve the derivative order carefully. So it's going to be M dotted with gradient, not gradient dotted with M. That would make things messy because the M is a constant vector, right? Once the charge distribution is known and you evaluate this integral, and that's constant, because it does not have any special dependence. That's just, quantity that's coming from the charge distribution. And so this, or the current distribution. So M is, you can't take the derivatives of M. So that's why you need to be careful when you are using back-cab rule, when one of the vectors is actually a del operator. Okay, everybody with me so far on that? What does this look like? Anybody knows what this is?
It will have Dirac delta notation.
It's going to be a Dirac delta function at the origin, right? Proportional to that because of the divergence R. Okay. Now, of course, we are looking in the limit of R much larger than R. So we are far away from the current distribution. So the contribution of this is going to be 0. That doesn't come into picture because we are far away from the point at R equal to 0. And so you only have to then do the second term, which is negative mu 0 over 4 pi M dotted with the del operator applied to R over R cubed. Okay. And then this part, I'm going to leave it to you to evaluate. You can do. So I will just kind of give you a starting point to evaluate. M dotted with gradient applied to R vector over R cubed. You can start with using the, so it's going to be Mi del I, and then you want to look at maybe just the, this is going to be a vector quantity. So let's say you want to only look at the kth component over R cubed is a constant. So it is essentially, you can think of this as RL to the power 3/2. And then let me move this so that you can see that the derivative actually applies to this whole thing. This is R. Okay, everybody with me? So I'm going to leave this for you as an exercise. We did a similar calculation for the electric case, so you can handle it. You have enough practice about it. And so when you do that, you will actually be surprised at the result that you get. It's going to be mu 0 over 4 pi. So that part is not surprising, but the other remaining terms that you get is 3 times R hat multiplied by R hat dotted with M minus M R cubed for r much greater than r, right? That's always important. You don't want to forget that. So this is the magnetic field that you get. Okay, what is surprising here? Does anybody remember what this looks like? So recall that the electric field, dipole electric field, was equal to 1/4 pi epsilon 0, right? So that's just the constant that you have, times 3 r hat dotted with p minus p over r cube. So isn't that kind of surprising? Because you have a completely different origin for the magnetic field. You have through a vector product of r cross j, you get the vector potential, you take curl of the vector potential, but the field that you get looks very similar geometrically to the field of a electric type, right? So if you were to make a plot of this, it is, in fact, you don't really need to do anything. It is going to look exactly like the dipole electric field that we plotted. I will just quickly remind you of what that looked like. I have not given you the Mathematica file directly, but I gave you a PDF of it in your lecture notes. And so make sure you try to regenerate those dipole field plots that we looked at. So you will see immediately what's going on here. So we define the electric field like this. Of course, what we did here was not use the expression that we got from the calculation. We kind of looked at electric field due to a single charge, and then we defined the let's see. Then we defined the electric field due to a dipole as two components added together, one electric field coming from the negative charge and the other one coming from the positive charge. And so you're not going to be able to do something similar for the magnetic field, of course, right? Because you don't have monopoles. There you will have to plot the field directly. And then here just the projected 2D plot, and this is how the field looks like, right? So it just rotated. And then we did we also did the calculation using the second method, which is the polar coordinates.
Dr.
So
Kapale,
here's, yes. Oh, you
share
cannot see
something?
it. Sorry, I didn't share the screen. Sorry. Yeah, here we go. All right. So we just to kind of recollect what we did for the electric dipole field calculation. This is the field due to a single charge located on a of value q, located at x0, y0, z0, and we are trying to find the electric field at position xyz. Okay, so that's just a general expression in the Cartesian coordinate, which then you can plot through a vector plot 3D, or you can project it onto a xy plane and then plot it in the 2D, or you can do a stream plot of it, which just shows you these radial lines that are coming outwards and so on. You can then plot a dipole field by doing a superposition of a positive negative charge and a positive charge, both situated slightly apart from each other. And then you are looking at the field at position xyz, right? But this does not quite capture the multiple expansion stuff, right? So, and here's the projection onto the 2D plane. So we know how to do that. We did a stream plot of the projection as well. Here is the real calculation, right? So we had this dipole potential, p cosine theta over r squared, right? So that's and once you have that, what you need is you can get Mathematica to evaluate the gradient. In our case here, you can write down the vector potential and ask it to calculate the curl, right? And so it would do that for you. Let's move forward. So You can calculate the divergence, you can calculate the curl, anything that you want. And in general, here we just kind of tested the divergence of E needs to be 0, and that's what it shows, right? So you can calculate it in the spherical coordinate system. Once you do that, you get, and then to be able to plot it, you have to transform it into Cartesian again, and so you get that. And then we did the contour plot 3D. Here is actually how it looks. There are some issues there because at r equal to 0, you're going to run into problems. But you can still see the plot. Here is the contour plot in the 2D plane. When you substitute y going to 0, and then we did the Cartesian representation, and then you can do all of this, right? So there are a couple of different ways of doing it. You can do something similar for the magnetic fields as well, right? So you have this PDF of that file as a part of the lecture notes for that day. You can try to replicate it yourself. And the reason why I did not give you directly the Mathematica file is then you won't struggle with the details of the mathematical steps, which is important. Okay, so that's the parallel between the electric dipole field and the magnetic dipole field. Everybody with me so far? Makes sense? Okay. Okay, let's now look at a alternate viewpoint on this whole multipole expansion business. And multipole expansion is crucial because that's essentially the most practical way of determining electric and magnetic fields, because we're always far away from the sources, right? So that's the thought behind that process. So now we're going to take a look at two different ways of doing the multipole expansion. Let's recollect what we did in the previous case. Okay, so let's start here. And the idea again is geometrical in the sense it applies equally to both electric and magnetic field situations, right? Because it's essentially looking at this distance parameter 1 over r minus r prime, absolute value. And we know from the Taylor expansion, it's going to be minus 1 over r minus r prime dotted with gradient of 1 over r plus half r prime dotted with gradient squared applied to 1 over r, and so on. And then alternate positive negative signs. That's because everything is in the denominator, right? And here, of course, we assume that r prime is smaller than r. That is crucial. And that's the Taylor series approach. First alternate method we are going to use is using the binomial expansion. And again, the idea is the same. We just take the same quantity, r minus r prime, and look at it as 1 over distance. You write it down using the Pythagoras theorem, essentially, which is going to be r squared minus 2r dotted with r prime plus r prime squared. Everybody understands why we have this thing here, or do I need to explain? It's just basically take the dot product of the vector with itself, square root of the dot product. And when you take the dot product of one component with itself is just going to give you these two terms, right? R with R, but there will be two terms where you have R dotted with R prime, right? And that's basically what it is. That's how you take a That's how you calculate the distance, right? So that's all there is to it. Then we take, again, the situation that r prime is less than r. If r prime is smaller and r is greater, you divide by r. So I'm going to take deliberately 1 over r common. And when I take 1 over r common, inside the square root sign, here I'm going to have r squared going in, right? And so, no, actually 1 over r squared going in, because this is in the numerator. Let's write it slightly differently. No, let me add one more step there, right? So that way you will kind of see what's happening. So what we are going to do is 1 over, if I take r common in the denominator now, we will be left with this r squared. When you take it outside of the square root sign, it will just now be left as 1, right? Because that r square has come out. For this term, you will have 2 r dotted with r prime times 1 over r squared, right? Because now we took r common, or r outside. So now this term has to be divided by r squared. Let's go further. And then the other term would be r prime squared over r squared. Everybody with me so far? Does that make sense? Okay, now that we have seen that, I can manipulate these things a little bit, right? What I'm going to do is convert them into the individual unit vectors. And so we're going to have 1 minus 2. The first one, 1 over r squared that we have, I take one of that r squared in the denominator and divide r vector by it. And so I'm going to get r hat. Okay. And then I'm going to do the same thing with r vector prime. I can write that as r vector prime as r prime hat multiplied by r. And then I had an extra multiplied by r prime rather. So r prime hat r prime is the r prime vector, right? So these two things combined, this here is that, right? And let's use the different highlighter. This is equal to that and 1 r remaining. Okay, everybody with me? You understand the color correlation there? And then what we are left with is plus, sorry, and then plus r prime squared over r squared raised to the power negative half. Okay, now do you know how to do these kinds of binomial expansion with negative powers? Have you done this before, or do you recollect? If not, it's a straightforward mathematics. So you can look up resources for it. I would suggest Wikipedia or Wolfram Math World. One of those is fine. But I'm just going to kind of give you a pointer here, which is if you have 1 over 1 plus z square root, okay, z is a small quantity, right? That's kind of what we are trying to do here. Think of this whole thing as a very, very small quantity. And so this here is the small quantity x, let's say, and this is going to be much smaller. So we're going to actually ignore that third term, right? So that's kind of the idea there. But let's write this down first. It is minus a half times z plus 1/2 times 3/4 times z squared minus and so on. And here we have minus 1 less than z less than or equal to 1. Okay. Everybody with me so far? Okay. So I just gave you the expression there, but it's something you can look up. It comes from elementary mathematics. The thing to note, and again, it may feel like a conceptual jump, but for that you have to do some of your own reading. So it turns out this particular expansion is related to real valued legendary polynomials. I got the spelling wrong. Okay, and then the reading assignment for you is the mathematics is discussed in Appendix G in the book. No, sorry, Appendix C in the book. There is another context in which you are familiar with legendary polynomials. If you have a 3D spherical coordinate system and you're trying to do the separation of variable techniques for the solution of the 3D spherical partial differential equation, right? When Laplacian is expressed in the 3D spherical coordinates, then for the theta coordinate, cosine theta, if you replace cosine theta as x, then you get legendary polynomials for that, right? So if you have, let's say, azimuthal symmetry, meaning there is no phi dependence, right? So you have, let's say, a charge distribution where it is uniformly distributed, but let's say the top hemisphere has a positive charge density because it's positive theta, and then the bottom hemisphere has a negative charge density. So you have theta dependence, but it's azimuthally symmetric, so there is no phi dependence. In that sort of a situation, your theta functions will be dependent on legendary polynomials of the argument cosine of theta, right? It's just the z projection that matters, right? So z or negative z. That's where these legendary polynomials come in, just to kind of recollect, right? So what we are going to do now is, instead of using this binomial expansion in that form, we're going to use it as 1 minus 2x t plus t squared. Okay, and you can see that this form that we have here, I'm going to use a slightly different highlighter. This is essentially this stuff here, right? It's 1 minus 2 times r prime hat dotted with r hat, right? And so that's that x. Then there is some other term, t, which is this r prime over r, and then you have r prime over r squared, right? So that's how that works. So let's actually identify them. So we're going to identify this as x, that as t, and this naturally would be t squared. So once you make those connections, then this is something that we are going to directly substitute. It's going to now be an expansion. So this function that you have, the function of x and t, it turns out to be an expansion in terms of the legendary polynomials. PL is just the index for the argument x, and t to the power n is what you need. So you can sort of see that it's just an expansion in that. And how do you know that that's true? If you take a look at, for example, the derivatives on both the sides for the correct coefficients of t, then you can, so if you take L derivatives, you're going to pull out PL of x on the right hand side when you do the derivatives by substituting, essentially t equal to 0, right, in the end. And you do the same thing on the right hand side, you will see that the coefficients match. That's one way of verifying this. I'm not proving this, of course, right? Right now we are not doing that. 0. So, but there are these limits. Absolute value of x is less than or equal to 1, and the limit on t is that 0 is less than t is less than 1, and which is okay, right? Because we have t is equal to r prime over r, and we are already in the limit where r is greater than r prime. That means you're farther away from the position of the sources. And so this is perfectly fine. It fits within those limits, right? So let's now recollect some of the important properties of the legendary polynomials. Any questions anybody has so far? So just in the interest of time is why we are not going through that mathematics. The math is not important. It's this conceptual new domain that it offers us that's important. And nobody does this in real life when you're working on things, problems like this. It takes years to figure something like this out, right? It's not something that happens immediately. It's not. When it's trying to understand things deeply mathematically, and you spend a lot of time figuring these kinds of things out. So there's a lot of trial and error and a lot of effort that goes into understanding these kinds of things. So we're not going to worry about that. But let's now, in general, though, something that would maybe help you appreciate this is whenever you have an orthogonal set of functions, you can expand some known functions into that orthogonal set of functions as an expansion like here, right? T to the L is just the coefficient multiplied by PL of X. That is a standard procedure for expressing a general function in terms of a function that you know the properties of. And the properties that are important are the orthogonality, which if you take two of the PLs, if they have the same index, then you get a non-zero integral. If they have a different index, then the integral is zero, right? That is their orthogonal, just like in the case. Okay, just like in the case of the unit vectors in a 3D Cartesian coordinate system, for example. And then another important property is completeness. So whenever a set of functions is satisfies these two properties, you can use them as basis functions to expand some other set of functions or express some other set of functions through these basis methods. Somebody said something. You have a question? Okay, maybe not. All right, so those are the two important properties, orthogonality and completeness. And you write them, because these are functions, everything involves either a summation like this here for summation over A or an integral over the argument X. Okay, and so just to recall, P0 of X is 1, P1 of X is X, P2 of X is half, 3x squared minus 1, and so on. So you can kind of see these are just polynomials. That's why we call them legendary polynomials. And so now, going back to what we were doing, which is the distance r minus r prime that we wanted to express. So I think I should probably just delete this. Make a longer one. Is equal to 1 over r. So that comes out. You can't play with that. That is always there. Then we do the expansion, L equal to 0 to infinity, r prime over r to the power L. That's our t. Then PL of r prime dotted with r. Okay, so that's our t, and that's our x. And this, of course, is true for r prime less than r. And so you will see that this is another expansion really for the distance parameter. It does not compare term by term with the multipoles that we talked about. So this works when we have azimuthal symmetry. Right, and we are taking the R prime parameter as some cosine in the it's similar to the angle theta, cosine theta in the spherical coordinate system. Okay. The utility of this is still kind of limited because what it depends on, okay, so let's say the crucial parameter here is x, which is R prime dotted with R, and which is equal to some cosine of the gamma angle between them, right? And so what we have, for example, here is, let's actually draw a picture that shows what's going on. So here's our origin. Here is the R prime, so that's a source point, and then somewhere far away is your R, and it's that angle between them, right? And I'm calling that angle gamma. Now, of course, as you're integrating and changing this, there is nothing sacred about this gamma parameter. The reason being, as R and R prime, both of these vectors are changing as you're analyzing the field at different points due to different source locations. And so it is in some sense awkward parameter. It's not something that is fixed in the first place, and so you can't really make sense of what is it that's really trying to tell you that expansion. And so as R and R prime are not constant vectors, they themselves change, and so the angle themselves change, and so it does not really make sense. What you want to do instead is take a full spherical expansion of the R's. So R vector basically involves R theta phi, and R prime vector involves R prime, theta prime, phi prime, and then use these as parameters instead, and then you're going to be able to do this. So we use something called a spherical harmonic addition theorem. There are certain specific ways of adding the spherical harmonics to arrive at the legendary polynomial. So spherical harmonics in general, YLM theta phi, are functions that involve both theta and phi, the two angular spherical coordinates. But if you involve both theta and phi. So what one ends up using is, again, your reading exercises appendix C. We will go through it quickly after we're done discussing this, so that you know what to expect there, so that you're not completely on your own. But it turns out with this, this R hat dotted with R prime parameter is not very helpful. Can we just translate it into not that dot product, but actual spherical coordinates of the two position vectors. And so it turns out you can do that, and that is done through this. So it's another expansion now. YLM theta phi are another set of orthogonal functions, and we're taking this PL and we're expressing it as an expansion coefficient in some set. Now, the only thing that's a little weird here is because the YLM theta phi have this e to the I m phi sort of complex term in it, and PLs are all real, so they are real valued, and so we need to do the expansion for over m equal to minus L to L, so all possibilities, and you have a complex conjugate combinations of YLMs, right? So you don't have just YLM because that would be complex. So you have YLM star YLM, and that's theta prime, phi prime, and then you have YLM theta phi. We have both of those coming in. One is the star, the other one is not. And that's how this thing works. And m of course is also an integer, as you know already from your quantum mechanics angular momentum discussion. That's where this appears as well. It takes any values from minus L all the way to 0 to L. To L plus 1 in number, right? That's how many values you have. Now, again, if you're doing this kind of expansion, you need the two important properties. One is the orthogonality, the other one is completeness. So let's take a look at orthogonality, how it looks for the YLM functions. So if it's orthogonality, you will have to do integrals over theta and phi, which is because there are no radial coordinate involved. It's essentially a solid angle integral d omega YLM. We could just write theta instead of theta phi, write omega. YLM star as a function of omega. YL prime m prime as a function of omega. That's going to be equal to delta L L prime, delta M M prime. That means you need both of them to be the same, L and M. Only then you're going to get a non-zero value. And then completeness. Since it has two indices, you have to sum over both of them. So you would be summing over L equal to 0 to infinity. And then for each L, you will be summing over M, which is minus L to L. And then you have the YLM omega, YLM star omega prime. And that will turn out to be a function of theta and phi. And it turns out to be sine of theta, delta of theta minus theta prime. Okay, here omega prime is theta and theta prime, delta of phi minus phi prime. Okay, so that's how the completeness looks like. And to recollect some of the small index values, YLM theta, when L and M are 0, it's a constant, 1 over square root 4 pi. Y10 of omega is square root 3 over 4 pi cosine theta. Okay, see how that looks? That already looks like the PAP1, which you know. And in this case, we can actually use the Cartesian coordinates also to represent this as C over R, because Z is R cosine theta. C over R would be cosine theta. Then Y one minus 1 of omega, this is M. Oh no, that's not how I should be writing down actually. Y L is fine, L is 1. I want to write both of them together, so it's going to be plus or minus 1. So that's M, that's L. And then it turns out the signs get reversed. The the real part of both the expressions is going to be exactly the same. And that is equal to now sine theta. And you have e to the plus minus I phi. So that's the complex part that I told you about. Or you can, if you wanted to write this in terms of the Cartesian coordinates, you can do that using the polar representation of complex numbers. You can identify this as x plus minus iy over r, and that gives you the at least first 3 or 4 of these spherical harmonics expressions. Okay, give me just a okay. So that's good. We have this kind of stuff. So we now know how to take this expression and replace the PLs in terms of the YLM. So let's go ahead and do that, and let's see what that yields. So it's now going to be 1 over r minus r prime. Distance is going to be 1 over r. L equal to 0 to infinity 4 pi over 2L plus 1. So that just comes from the expansion coefficients. Then you had r prime, the t to the L, right? So it's r prime over r to the power L. Then you have sum over, so the PLs have the sum over m equal to minus L to L. And then you have the YLM star of omega prime, and then YLM of omega, right? So omega prime is theta prime, phi prime, and this one, again, the same condition is true, r prime is less than r. Okay, I'm going to put a box around this. Now, the nice thing about this is, even though we did this exercise for r prime less than r, there is a way you can make this expression valid in the opposite limit of r prime greater than r, right? So if we take, if r and r prime are interchanged, then the expression, then the expression would be valid for r prime greater than r, right? That condition has to would get reversed as well as you're doing that. And so what we can do is we can actually write, so the Taylor series expansion work that we did, we don't have such freedom there to be able to just interchange those and get a different expression for the 1 over r minus r prime distance parameter. But this way of expressing it, you have the ability to reverse, and you can actually make a much more general expression. You can be far away from the charge distribution, or you can be inside the charge distribution, and you can determine the fields near the charge. So you can determine both the near field as well as far field. You can't do that with Taylor series. So that's the advantage of doing it this way, right? So let's now write down a general expression. So we take r greater to be greater of r and r prime, and r smaller be the smaller of r and r prime. Okay, so that's just the notation. And you can see just because we are going to replace. So in this case, you can see what goes in the numerator here is the smaller quantity, And what goes in the denominator is the greater quantity, and that just generalizes that expression. So in that general sort of framework, we are going to have now r minus r prime distance will be the same as r prime minus r distance. The distance is the same, the order does not matter there, and that's why we are able to combine those, right? And so you get the term that comes out here is the quantity that's greater, so it's going to be 1 over r greater than the summation over L 0 to infinity, the coefficient 4 pi over 2L plus 1, then the t to the power L, which involves r less over r greater to the power L, then the expansion in YLMs minus L to L, YLM star of omega prime. Actually, not omega prime anymore. It's now that also has the indices less and omega greater, right? So smaller and greater, those two things are needed there. So whichever is the region you are interested in, inside the charge distribution or outside, you would use the corresponding expression for it. So this is the most general expression that you can write down. I'm going to just move it slightly here so I can put it in a box. Okay, so let's make use of it, right? Without making use of it, you won't really see the power and the usefulness of it. So let's apply this to our first the multipole expansion problem, and then we will look at something called the interior expansion and exterior expansion. So this is the advantage of doing this. You're not only restricted now to finding fields far away from the charge or the current distribution. So these are called spherical and azimuthal multipoles. The earlier multipoles that we found, those are essentially the Taylor expansion based multipoles. E bar r minus r prime r. Okay, so that's how we write down the potential. Since we have the expansion for r minus r prime, we can substitute that in there, and that will give us the coefficient, right? So first, let's just say we have these two regions where r is much greater than r prime, that is exterior, or you have r less than r prime, that means you are at distances that are smaller, so it's interior. And I should probably show you how this thing works, right? So we're going to assume that the charge density is in such a way, I'm just going to use a different color here. So here is the charge density, but there is some exclusion region in the center. And let's see, what color did I use? Okay, so we'll use the same highlighted. Okay, so the shaded region is where the charge density is located, right? And we just deliberately created a hole inside, so it's sort of like the donut shape, but again, somebody didn't do a good job of making a nice symmetric donut. And then what we want to do is there are clearly now two different regions, right? One region that's exterior and one that's interior. So if that's the origin, if you're here, that's exterior. And if you are inside. So I'm going to now just draw a dashed sphere that would sort of fit into this area here. Let me make it as big as possible, but it's completely within that empty volume of space. The radius of that dash sphere is capital R, and your observation point little r could be anywhere inside there, and that is interior. Okay, and so you have this sort of a situation. I'm just going to put this drawing here so it does not get mixed up with the rest of the material. Okay, everybody with me so far? And so rho is completely outside the sphere of radius r, right? In that case, it makes sense to do that, right? Imagine a spherical shell. So you have a spherical shell and you want to find out the potential inside and then potential far away, right? You could use these types of ideas to figure that out, right? So let's now calculate the exterior spherical expansion. And we will do similarly the interior spherical expansion. And this we are able to do without really having to do any sort of Laplace's equation solution, right? So these methods are not the boundary value methods yet, right? So these are simple methods that we're using. L equal to 0 to infinity, m equal to minus L to L, ALM, YLM, omega over R to the power L plus 1, R much greater than R. Okay, so that's how that looks like. So we just did this expansion of 1 over R minus R prime, substituted it inside, and then introduced a expression for ALM, right? So let's see what this is. ALM, which are the exterior, these are called exterior spherical moments. And they are now 4 pi over 2L plus 1. That was the coefficient that we had in between there. And then you just do the, remember the moments are some integral over the source charge distribution, right? And so you just take all of the R prime dependent terms, combine them together, and then that's going to give you this. So from the T to the power L, we only pull out R prime to the power L, R to the power L goes there. And then you had the 1 over R extra outside. That's why this becomes R to the power L plus 1. YLM stays as the expansion coefficient there. It does not appear in the spherical moments, but YLM star goes into the spherical moments. Everybody okay with this? If you just take this, plug it back in there, you will see that it matches with what you would get from there. Okay. And in general, ALM would kind of have the dimensions of the charge, distance to the power L, and so that would cancel with the distance to the power L plus 1. You know, the L power would cancel. You would have 1 over R essentially for the different terms. Another important property to note is the YL minus M of theta and phi is equal to minus 1 to the power M YL M star theta phi. So there's this extra sign change that occurs, but YL minus M is proportional to YLM star. Right? So you can kind of see how this process works. Okay, another thing, you have this expansion that we did in terms of the Cartesian coordinates using the Taylor expansion. Here now we are doing it in the spherical coordinate system. And so how do those two things relate with each other? It turns out, if you look at coefficient of 1 over r to the power L plus 1, that is identical, right? Identical to the corresponding coefficient in the Cartesian expansion. So you could take the Cartesian moment and write it as a linear combination of several spherical moments, right? That is something that's easily possible. Okay, everybody with me so far? Makes sense? So this is exterior because we chose r prime to be smaller than r. Now let's take a look at the interior and see how the expression changes. Anybody has any questions before I go on to the next step here? Okay, no questions. So again, the idea is the same. 1 over 4 pi epsilon 0, sum over L, sum over M. Okay. Then the coefficients BLM, that's the integral over the charge distribution, r to the power L, y, L, M star of omega for r less than r. So this is interior. We are inside of that sphere of radius, imaginary sphere of radius r. And of course, then you need to specify what the BLMs are going to be. The coefficient does not change. 2 pi, 4 pi over 2 plus 1. You have, of course, the integral over the sources. So this part is easy to understand. How does the rest of the stuff change? So that's where things are a little different, right? See what happened? Let's take a look at this situation here. You had ALM divided by r to the power L plus 1, okay, for the exterior moments. You can't have the distance in the denominator when you are inside. When r equal to 0 is part of the domain, that would put you in trouble, right? And so you have, when r can go to 0, you cannot have r in the denominator. You have r to the power L here, right? So that's the position dependence has changed now. And you have here r prime to the power, r prime to the power L plus 1 would go in the denominator here. So the r and r prime essentially interchange their roles. Okay, so that's how that happens. And let's actually copy this to see the comparison between the two. So recall that ALM was like that, and see what are the differences between ALMs and BLMs, the interior and the exterior moments. Coefficient is the same. Volume integral is over the charge distribution, yes, but the thing that changes is the y's are different. Right? So I'm just going to use, maybe dashed lines to point out. This star is different. There's no star here. And the distance parameters are different, right? So in one case, you have r prime to the L for the exterior moments. And for the interior moments, you have 1 over r to the power L plus 1. and then YLM versus YLM star. Okay, so that's how these two things are different. Everybody with me? Does that make sense? Okay, so now I said, if you have azimuthally symmetric charge distribution, you don't really need this e to the im phi terms because there is no phi dependence. So eventually all of this should basically boil down to only needing legendary polynomials, which are the functions of cosine theta. Of course, not in the form that we saw earlier. That was a legendary polynomial involving the angle between the two r and r prime vectors. Now we want them to be individual, so it's going to be products of these. So let's take a look at azimuthally symmetric charge distribution. So we are going to encounter something called azimuthal multipoles. Okay. So no phi dependence. And when can we have that? It depends completely on the charge density. So if for azimuthally symmetric charge density, right? Anytime you have some sort of a symmetry, it gives you some mathematically equivalent statement about what's happening. And so in this case, it's going to be no phi dependence. If you have an infinite plane in a 2 dimensions, that means it does not have any z dependence, those kinds of things, or it cannot have any, or rather it will. The field will have z dependence. It cannot have x and y dependence because x, y things are going to infinity. And so what we have here is rho r prime, theta prime, phi prime is basically like projected out the phi, and so it's only function of r prime theta prime. Then that means YL, M is always 0. Theta phi, M equal to 0 always. And so that means it's just going to be 2L plus 1 square root over 4 pi PL of cosine theta. That's how it's going to look like. That's how the YL zeros look like. No e to the im pi. And then you can look at the normalization slightly differently. D phi YLM theta phi is going to be square root of 2L plus 1 over 4 pi delta m0. Right? That's where it comes from, really. What we're basically doing is you do the integral of YLM theta phi over phi at sort of average out things. The normalization there is 1 over 2 pi, and it just gives you that. So you can take this, plug it back into this ALM, BLM functions. M is 0 now, right? So there is going to be a slight change in the terms in the front, right? So what basically happens is ALM would become AL delta M0 and sorry, M0. Why am I writing that? Okay. And the coefficient, this 2L plus 1 over 4 pi that comes out of that integral, that needs to be carefully carried over, and it just comes in the reciprocal here. Okay. And then BLMs would have something similar. Now, because M is 0, you only have to carry one index for the azimuthal moments, AL and BL. And the coefficient is the same for both of them, right? It's that extra stuff that comes out. Okay, and then write down what ALs are. AL is, again, the volume integral, d cube r prime to the power L, rho of r prime, PL cosine theta prime. And BL is going to be similar, d cube r prime, rho of r prime theta prime. Actually, I should have written down its function of theta prime as well. And then in the denominator now you will have r prime to the power n plus 1 PL cosine theta prime. Okay, so that's AL and BL. I'm going to put them in one box together. So these are both interior and exterior. You need to not confuse them with what is exterior and interior. Confuse between them. Confusing between them is not a good idea. You need to always be careful what's happening. And there is an easy way out to see that, right? R prime is R prime. If you're trying to find the exterior moments, R prime can be 0, right? And so this is okay. That will be finite. And so that's the exterior moment. If you're trying to find interior moments, then R prime cannot be 0. And so you can have R prime in the denominator. So that's the interior moment. Okay, so that's how you can, just by looking at the expression, you can figure that out. Give me. Okay, so what we're going to do now is write down, these are just the moments, write down the potential in that case. And then today we won't have the time, but in the next class on Thursday, we will look at examples. Without examples, you won't see, why did we do all this stuff? What's the use of it, right? There needs to be a couple of illustration of why these things are useful. So let's look at the potential, how that looks like. So 1 over 4 pi epsilon 0, of course, is common. There is whole parallel argument that you can make for the magnetic situations as well. R is greater than R. And Pradeep, you may remember you had a question last time when we started discussing the magnetic situation. Where are the legendary polynomials coming from? This is where they're coming from. PL R to the power L, PL cosine theta, R is less than R. Okay, and so you could see by looking at that, AL are the exterior moments, BL are the interior moments. One should know those, how to calculate those, plug them in, expand over them, and then you get the total field. Okay, everybody with me? So we will connect this with the stuff that we have been doing so far in the Cartesian coordinate system later on. For now, what I want to do is quickly show you the appendix so that you know what sort of mathematics is discussed there in Appendix C. Let me share the screen with you. Okay, so you can see the screen hopefully. So that's the Appendix C on special functions. And the stuff that we just did today, they're just giving you the real valued expansion. 1 over square root of 1 minus 2x t plus t squared. It can be written down as that. Where does this come from? It basically comes from the differential equation. So that's the legendary differential equation. PLX are the solutions. And then the Sturm-Liouville eigenvalue problem, those of you who took the math physics class with me last semester, you have seen this stuff. Those of you who did not, you will see it eventually, right? So the order of seeing things may be a little different, but you will see them. So what we are looking at there is, you are familiar with the matrix diagonalization problem, where you, just like we talked about the moment of inertia tensor or the quadruple tensor, you can diagonalize them and only diagonal elements exist, and then you get the corresponding eigenvectors. The same kind of approach. So matrices are the operators in the vector space. Now, if you generalize the vector space to include not just the individual numbers in a column vector, but a function space, right? So then you can think of the differential equations themselves as operators operating on this function space. And so you can use this idea of orthogonalization to the derivative operators themselves. The process is slightly different, but the idea is the same. And then the eigenvectors that you're going to get, they form now the basis set for this function space. So just like x hat, y hat, z hat are the basis set for a three-dimensional vector. Same way, the solutions are the eigenvectors of the eigenfunctions of the eigenvalue problem are now orthogonal. If you need to make them orthogonal and complete. Once they are, then they become the basis set. That means any arbitrary function that's valid over that domain can be expanded out in terms of that. So that's basically the idea. You can go through the mathematics. Once you get the concept, the mathematics is straightforward. And that's the idea behind all of this. Okay, and then the slightly different differential equation gives you the, so where the m is not 0, that gives you the associated legendary polynomial. So you need to split the two parts, and that gives you the YLM theta phi's. So you get the PLs for the theta part and the y, in fact, actually, in some cases you have to combine them, but this is what it is: the PLs and so on. So we saw these types of expressions, their completeness, orthogonality. It's all discussed here, and then some of the expressions for the few small spherical harmonics are given there. Bessel functions, when you have a cylindrical symmetry, then this is the differential equation that you're going to get. When you take the Laplacian, express it in the cylindrical coordinate system, this is what you're going to get. And so you use those as your basis sets for expanding. And the coefficients in that expansion, they will be determined by the physics, right? So we will take a look at some of the problems later on that involve this. We will actually not be doing many spherical problems because that's straightforward. You have seen many examples of that. We will actually do some couple of basic function problems just to help you develop comfort with Bessel functions. And so feel free to read through the Bessel function properties and such. There are Bessel functions of first kind, Bessel function of second kind, and then there are combinations of the two. So there's just whole host of these. These are called the Hankel functions, which are the combinations of the two. And they're very, very useful in variety of different situations. And this is kind of important, right? So the e to the ikr type terms you get when you go from statics to dynamics, when the waves are actually propagating, these light waves, that's where you get this e to the ikr type phase term. And that also can be expanded into the spherical harmonics or the Legendre functions or the Bessel functions. And that's kind of what you see here. In fact, it's a combination of Bessel and Legendre polynomials. And that's that. And those are just provided as identities to you. So we do need a lot of mathematics help for this. And that's, we're not going to ask you to remember that. Anytime you have to deal with this stuff, you will have the resources available. So you just have to develop comfort with it. You don't go by the approach of, okay, I want to derive everything. In this case, it's not necessary. It's there. You just need to know how to use it and what motivates the use of Legendre functions versus spherical harmonics versus Bessel functions. You want to develop that intuition, not so much where they come from, really, which in some cases you have already seen that they come from the solutions of the corresponding differential equations. Okay, so that's it for now. I went over a little bit, but that's where it is. You don't have to worry about a homework from a week from today. Next Thursday, you're going to do the presentations. So do a good job on the project, and then I will assign the homework after that, and you will have time to practice all of the stuff that we have done in the class. Remember, the purpose of the homework is essentially to practice things that we have done in the class, and so you will get that practice. Any questions anybody has?